Good afternoon, everyone. Welcome to this NITheCS Colloquium. And today we are very happy to have Deshen Moodley with us, who will talk about artificial intelligence for sustainable development in South Africa. And Deshen Moodley is associate professor in the Department of Computer Science at UCT and co-director and co-founder of the South African National Center for Artificial Intelligence Research, also known as SIRE or CARE. His research lab, the Adaptive and Cognitive Systems Lab, explores different artificial intelligence techniques to create a cognitive and adaptive systems in diverse domains, including health, energy, finance, Earth observation. He's currently investigating architectures and methods for combining logic-based software agents with probabilistic and machine learning techniques in the real-world decision-making systems. And moreover, in 2021, Deshen was selected as one of the 19 fellows for the 4th Intercontinental Academia on AI. And he's the only fellow of this academia, which is based on the African continent. Thank you very much, Deshen, for agreeing to talk, to present to us your research. You are welcome to take this in. Thank you.
Thank you, Ilya, for the introduction, and thanks for inviting me. So I'll be, as Ilya mentioned, I'll be talking a little bit about AI for sustainable development, and it will have a South African flavor to it. Which is what my research is definitely grounded in South Africa. So I have 4 parts to the talk, and the first one is about to introduce you to augmented AI systems. Then I'll give you an application perspective, and I'll talk about a few kind of real-world systems that we've tried designing in our lab. And I'll go on to talk a little bit about AI for sustainable development, to take a kind of holistic view, and then some views on creating a national AI ecosystem in South Africa. So this notion of augmented AI so this is just a definition. It's a design pattern for human-centered partnership between people and AI, where we work together to enhance cognitive performance, including learning, decision-making, and experiences. And so this is slightly different from what people were thinking about in terms of AI and its goal over the last few years, where they were looking at more the kind of autonomous AI, where the AI is going to work, or the AI system is going to work independently of the human. So in terms of computer science and AI, there was always this quest for full automation. So, you know, at the abstract level, a computer is of course a machine, and machines are meant to automate. So this is where the deviation between traditional AI and augmented AI. So with augmented AI, you leverage both strengths of the human and the machine. And this can be seen as being a lot more powerful than just the human and just the machine. So the AI must learn to adapt to the user, the human, and the human must learn to also adapt to the AI. And this constant learning of each other should amplify and empower and create a more powerful kind of augmented intelligence. So the word here is that the AI, or the important notion, is the amplification rather than replacing. So augmented AI intends to build machines that amplify rather than replace the humans. And in this case, it's the cognitive power. So if we look at this interpretation or perspective of AI, we can look at 2 challenges that emerge from this perspective. And of course, this is linked to what the challenges. These challenges are also similar to some of the more general challenges versus AI. So the one is adaptation. As I said, the human must adapt to the machine, and the machine must adapt to the user. But the machine must also learn to adapt to a dynamic world. And in physics, lots of mathematical and physics problems in physics are about dynamical systems. And this is not always hard, always easy to model and update. So learning in a kind of dynamic environment can be quite challenging. And this has got to do with machine learning or model learning, and then when to and how to update the model, and to kind of relearn or refine the model. And then from the user side, the user is, as I mentioned, adapts to the machine, and the user also evolves. And so the user might have changing goals and tasks, and these might also be vague. So how do you specify this, and how do you evolve these kinds of tasks, or kind of get clarity to the task specification by this kind of human-machine interaction? Also, the user's ability, knowledge, and skills will evolve. So this can be seen from what we call the knowledge-driven side. And then linked to that is the notion of cognition. It's about how to represent this knowledge, and how to, or thinking as we know it more commonly, how to make inferences using this knowledge. So representing, acquiring, and then updating and evolving this kind of knowledge or knowledge base that's created. So this process, also including the more challenging task of discovering new knowledge, is called the epistemic process. And of course, this discovery of new knowledge is quite hard. I mean, this is what we are concerned with as scientists. So is augmented AI, is this notion a new notion, or has it been around for a while? So of course, it's getting a lot of prominence now, but it actually is not entirely new. So depending, even the broader notion of AI, people would say, well, actually machine learning and neural networks has been around for 40 years. But what has changed? So it's worthwhile just mentioning the semantic web wave, and I call it a wave because it's quite powerful. It came in and it was going to create a lot of momentum, very similar to what we're seeing in terms of the momentum that deep learning is gaining. So this was in the early 2000s, and this is a kind of knowledge-based AI approach. There was these notions of intelligent software agents, and the idea was to make the web machine interpretable, to use these things called logic-based ontologies, where you'd add semantics to basic concepts and relations that you'd see in web pages. And if you could do this, then machines or software agents could interpret and reason, and then combine, analyze, and make sense of these of all the content on the web. It produces lots of language, many languages, tools like the web ontology language, the semantic rules language, and some query languages, and a lot of these are still around. So one of the things that is quite prominent now is the notion of knowledge graphs, and of course, intelligent software agents are still around, and it has its roots in this community. So in the early 2000s, the semantic web elevated the knowledge-based approaches, and it was very focused on creating human-centered AI systems. The whole notion of ontologies was to be closer, to take the logic-based approaches closer to how non-computer sciences and non-mathematicians could represent and access this knowledge. So there was a lot of hype, and people would say at the end, they said, okay, it was just another hype cycle. And one of the issues that came up with is that it was very concerned with creating these ontologies, but it didn't really, I think at its peak, it didn't focus on the actual application and use. And towards the end, there were some key researchers that wanted to focus on this, but I think that it had run its course. And so now most people have never heard of the semantic web. So these scientists mentioned the notion of the pragmatic web, which is builds on the semantic web. One of the other things that came out of it is this emphasis on interoperability. So you had all these its web pages and systems that had all this data, and we needed to agents or these systems to communicate, and the notion of interoperability between systems was also elevated. And ontologies allowed for semantic interoperability because you had these kind of logic-based approaches to define concepts and relations. So that means one representation in one database could actually be mapped or aligned with another representation in another database, and then the systems could talk to each other. But as I mentioned towards the end, this notion of the pragmatic web came up, which was supposed to sit at a higher level in terms of communication. And this, of course, didn't gain traction, and the hype cycle was over. So unfortunately, this fizzled out. So these levels of interoperability comes from semiotics. And I still think that this is where this pragmatics and this kind of social world level is where human-centered AI and augmented AI systems need to focus on. This community also produced different types of agents or agent architectures. It was the kind of reactive agents. Those of you who know Daniel Kahneman, he has this book out called Thinking Fast and Slow. And it's about how humans, the reasoning processes or thinking or cognitive processes. So this thinking fast is kind of reactive, reflex type of thinking that we do. And of course, we have also deliberative, like slower type of thinking, where we really think more deeply and take more time to get some consistency and explanations and so forth of what's going on in the world. So these two types of agents were proposed, and of course, if we want to align with human cognitive processes, then you actually want these hybrid systems. So hybrid agents, which can do both the thinking fast and the thinking slow, to align with how we as humans think. So where are we currently with this notion? So AI systems have gained now a lot of traction, and this kind of how do you design them, how do you develop them? So there has been some work. So here's some challenges that one of the researchers in this field, it's interaction with raw and heterogeneous data. So this is is linked to interoperability, uncertainty, how to represent it, express it, and reason with it, the learning part, which I think many of us who have worked in AI know about machine learning, and then the specification, high-level abstractions for specifying requirements for an application. And then, of course, this is more for software engineering aspect, is to be able to actually reuse models that we build and to chain components, software components, and to come up with these kinds of pipelines where you can swap out components quite seamlessly. Just for those who don't have a computer science background, in software engineering, there's just some, if you're talking about designing systems, just as a refresher, and this is the perspective that I'm taking for the rest of the talk. When I mention the word architecture, it's a software architecture. We talk about the layout of some complex computer system or information system. And one can think of this as a blueprint in the same way that you have the architecture for a building, which is a blueprint, and then the implementation is actually the builder building the structure according to the blueprint or the architecture. And this is, if you want to create, if you have a team of software engineers working together, the architecture is very important because it sets out the abstract design of the system. So when one talks about a pattern, it's usually at this level, it's the architectural design pattern. And this is quite a well-researched area. There's even languages like the architectural description language for describing architectures. And the notion of a framework, sometimes called an application framework, it includes the architecture, but also the tools and the methods for building certain types of software systems. And in this case, we'd want to talk about intelligent systems or augmented AI systems. So linked to this thinking fast and slow, there's also, as I mentioned, there's a lot of work in this area. And there was one from 2 years ago came up with this idea of machine thinking fast and slow. A lot of this work emanates from the cognitive sciences, and they showed how the developer and the AI system and the user would work together. And this is the notion again of an augmented AI system. So now I just want to move into some concrete applications, and these are just to give you a flavor of some of the work that we've done in our lab, and especially the ones that had some kind of development or social good aspect. The way we look at sensor-driven systems, and it's linked to this notion of the Internet of Things, but it's more broader than that. So you'd have some environment, you'd have some sensors that are in this environment. It's a dynamic environment. And then you'd have some tasks that you need to do. So it could be just monitoring, but maybe it could be monitoring different types of things like air quality or the weather and what people are doing. And then, of course, some goals or tasks that you want to do, like what decisions do you want to take? And then, of course, you can predict what's going to happen. You can model and start predicting what's happening in the world. So this is due to Adeleka's work. He did it for his PhD in the lab. And this was in the south of Durban. There was, in the south of Durban, there was, in the residential areas, there was a problem with air pollution. And this was causing some adverse medical conditions, especially some respiratory problems. So these are households. There were 3 households, and he deployed this low-cost sensor platform. He took some readings, some sensor observation readings. This is air pollution, particulate matter, and yeah. So and then he created this kind of distributed system. And just in terms of the architecture, which is what we designed, there was a monitoring layer which collected all the observations. And then there was another layer for situation analysis, both to detect adverse air quality situations in the household and also to predict what the readings are going to look like, and then what kinds of decisions we could take or interventions and actions we could take. So in this architecture, there was a lot of data processing because we had these streaming data coming in, continuous data coming in. There was some noise. You could use machine learning to do situation prediction, model learning, and ontologies we used for situation detection. And I'll show you an example of the ontology we created. And then at the higher level, to incorporate uncertainty and some kind of causal knowledge, we could use things like Markov decision processes or Bayesian decision networks. And this gives you an idea of how you could use this kind of knowledge-based AI and the machine learning, and how you could create systems that incorporate both of these. I'm not going to go into too much detail. This is a little bit of a technical slide, but there's the observations coming in, and it was in 1 minute intervals. And then we used some air quality indexes to turn these the numbers into qualitative values to make some assessments like good or poor. And then we use the machine learning, like a neural network, to actually build a model based on the signal to predict future signals. And then we combine these, and then we could decide what the situation was and what's kind of the sequence of actions that are, or interventions that should be taken. This is the ontology. Again, I'm not going to go into too much detail, but this was a kind of specification of the domain concepts, how everything fits together, and at all different levels, from the data level to the knowledge level, and one can then extend the system or allow it to interoperate with other systems or integrate other types of data into the system. So a completely different application that we've worked on is domestic electricity consumption. And the problem here, and this is based on a South African data set, so energy planners, they need to understand at different types of households, what's the daily consumption behavior for electricity usage, and they use this to do long-term planning. So they construct these, what they call representative daily load profiles. So there's an example of a representative daily load profile for a lower middle class household in KwaZulu-Natal for more than 7 years, and where the household had more than 7 years of electricity. And then it's got, because there's a differentiation between seasons and type of day. So a typical summer Saturday, what it would look like, Sunday, a weekday, and so forth, and the same for winter. So they construct these, and then they can do aggregate depending on the households in types of households in a particular area. They can then do aggregated expected consumption, and then know how to do the planning for electricity consumption. So of course, in South Africa, we have the households are highly variable. There's huge amounts of diversity. And so this is it also changes over time. And the experts take a lot of time to actually put this together. And it can, several years may pass before it's updated. And then of course, you're doing planning based on outdated. Entire suburbs may change drastically in terms of their demographic. So we explored how AI can be used to automatically construct these representative daily load profiles from the data. My master student, Vipka, she actually was working for the Energy Research Center, and she was curating this massive data set. If anyone's interested in it, you can access it. You can read the paper, and there's a link to access the data set. It's roughly 15,000 households over 20 years with 5-minute readings. So she used a cluster analysis, and we had some general cluster analysis, clustering metrics like DBI, MI, and silhouette index. But we found that this just picked up arbitrary patterns, and the experts they actually were looking, it was a subset of patterns that they preferred over other types of patterns. So we had to actually engage with the users, domain experts, and find out how to represent their scoring system, because these metrics, you could score different cluster sets using these metrics and know which one is better than the other. But the experts also had their own preference, and we needed a way of understanding how the experts, which ones they preferred over others, and we came up with what we call external metrics using a cluster scoring metrics. So these were qualitative measures that we came up, and we kind of human and application dependent measures, and they were about expressivity and usability in that domain. So we used this methodology of using competency questions, which came from the ontology community. And we found that if we just picked the clusters, the best cluster set based on just the usual metrics, the cluster analysis ones. We got a certain set of clusters because it was just any pattern, and it optimized according to that. But this was more guided to incorporating expert preferences and how the experts viewed the world. So these were definitely a lot more usable using these. So doing it without that, we got one set of clusters, and doing it with that, we got one that was a lot more acceptable to the experts. So this showed how you can take domain knowledge from users, incorporate it into a classical machine learning system, and then create something, a set of patterns, in this case, that's a lot more usable by the experts. So using this approach, we reconstructed these, and this is an example. This was the one that the experts constructed over many years. And ours wasn't exactly the same because it also took in the variability over the years. And the experts actually found this quite interesting and usable in terms of their planning. So those were two applications, one in air quality monitoring, indoor air quality monitoring and electricity. And another application we're working on, which is, I would say, the holy grail of AI, is to automate knowledge discovery and evolution. Some attempts have been done. So there's something called the robot scientist and the automated statistician. But of course, this is hard. And I mean, this is the ultimate is to automate the very process of science, which I think is, that's definitely very blue sky. So we drew from philosophy of science, a theory of method from there. It's a newer theory of method. It's called the abductive theory of method, ATOM. And we found that this ATOM, the abductive theory of method, was very, had some alignment to these two kind of top-down AI and bottom-up, the data-driven and knowledge. So ATOM had two main parts or processes in knowledge discovery. It was phenomenon detection, and that's the machine learning is really good at pattern detection. And it also had the what it called theory construction. So when you see a pattern, you can then say, is it a kind of expected pattern? Is it a novel or new pattern? And if it is, what's possible explanations? And then if we see this recurring, can we create some hypothesis and maintain these hypotheses in weak theories, and then check these constantly until they become stronger. Some theories get weaker and fall off, and other ones get confirmed and become stronger. And we use these ontologies, a combination of ontologies, rules, and Bayesian networks, which is the kind of causal knowledge to represent causal knowledge, and we came up with this architecture. So you can do model building with machine learning, you can do the situation detection and analysis to perceive or interpret what's going on, some deliberation with slow thinking, and then this was the harder part, which we're still currently working on, is about how to do the automatic hypothesis generation. So we have some preliminary results, and I'm not going to go into too much detail. So we're investigating this for a personal health agent using wearables. Again, lots of data coming in, lots of knowledge, and how do we combine this kinds of models that's coming in from the sensors and wearables, like the ECG signal. How do we detect anomalies or poor health conditions, and then how do we interpret it and find out what's the causes of it? So a lot going on, and but of course, both the knowledge base and the data-driven AI can help with that. So this is really what we're very interested in. It's to create this kind of augmented AI system for knowledge discovery, acquisition, and evolution, and this is a work in process that we have. So I skimmed through this because I want to get to the next part. So just some concluding thoughts about parts 1 and 2. There's a fine line between automation and intelligence, and the interesting thing about AI is that I notice whenever I speak to people about where AI is now, where you're using AI. They always think they are not, but actually they are using sophisticated AI, like Google Maps, your predictive text in your SMSs and WhatsApp messages, Siri, and so forth. But we always think of AI as something that's new and novel and something esoteric. So I think as these kind of older AI techniques become more established, they'll become part of the normal computing algorithms, the automation side, and they will always be looking at pushing the boundaries to mimic harder tasks that humans can do. I believe the humans working closely with machines will produce better systems from so many different perspectives. And of course, the exciting aspect here on the technical side is creating systems that can automate knowledge discovery and knowledge generation. So now to talk about, I have mentioned some parts about where we're using AI for development and in energy, and some touched on wearables and air quality monitoring, which is linked to health. But this is now, I think, sustainable development and where the sciences, especially AI, efforts into it, is quite topical. And there's been now quite a few papers and quite a few positions taken on this. So here's something very recent in just a few weeks ago from the World Economic Forum, which says that even though it has all this potential, it's of course, which is unsurprisingly, it's mostly driven from the commercial side, and the WEF says that there's actual implementations in development are quite rare, the use of AI in this area. And they came up with 3 strategies. So promote external development, especially in developing countries. These development, like NGOs and government, they don't really have the skills. So they should actually create these kinds of open innovation ecosystems and partner with people outside government to do this. And this seems sensible. The skills, that's always, I think that's again, not surprising, especially in our context in a developing country. High-end AI skills, that's something that we need to build. And promoting an entrepreneurial culture to leverage AI, because there's a lot of excitement, lots of potential, but you need people who are willing to take the risk and to embrace and champion it and explore where this what can be done with AI. So another paper which looks at more broadly, not just AI, but digitalization. And again, it's a similar, it seems to be untapped. It seems that lots of potential, of course, driving or investing in AI for social good needs huge amounts of funding. It seems a lot of the funding is coming from the commercial players like the big tech companies, venture capitalists, but again, that's for commercial gain. So a lot of potential, but I think it's under-resourced, and I think there's a lot of latent power or potential that one can direct using AI. And then I just want to mention one more recent paper. And this, if you're interested in this, they also had they took each of the sustainable, the SDGs, and they looked at the positives and the negatives in terms, because AI doesn't only have the positives, it can cause huge inequality. And there's also some risks with all the computing resources. There's some risks to the environment. So this provides a really, if you're interested in this, there's some nice analysis they've done for each of the SDGs and what's the positives and the negatives of AI. But the one issue is that AI-powered technology could possibly cause a lot of inequality. It could actually enhance inequality and wealth distribution. So we just need to be quite, I think, vigilant of that. We also did a short position piece in our group, which is pretty much a lot of these ideas in this talk comes from this. It was just a 2-page, like where's AI heading and what should we do about it? And I'm just going to talk a little bit more about. And again, these are just my thoughts and to start and stimulate a discussion. So what should we do about it? And I firmly believe that in South Africa specifically, the idea of creating a national AI ecosystem seems to be quite a reasonable way to move forward. We could use it to develop skills, have a long-term skills development plan. It could create a platform and forums for industry, governments, and academia to talk and discuss and direct the development of AI, and I think that's quite important. And one must also remember, I touched on this earlier, that it's quite a dynamic field. So one can't spend 2 years putting a plan in place and then execute it for 10 years. It needs to be agile. So you need these forums that are always there, be persistent. And if one sets these kinds of infrastructure up, we can also focus on broad-based reskilling, make AI more accessible to a broader community. And this is already happening on the global, like with open source platforms like TensorFlow and PyTorch, and all the huge amounts of material that's out there. But we could actually pick certain types of platforms that we think that make sense for us and build up expertise, and then you can have a more broad-based access and skills development plan for in those areas. If we don't do anything, I do believe that if we just leave it to evolve in an ad hoc manner, then it will be driven by mostly commercial interests. The people who know how to use AI will dominate it, and it will become more expensive I think it becomes more proprietary. So we just need to be quite sure of that. And how would this connect with what's going on nationally? So the Department of Science and Innovation have just recently launched the start of what they call the decadal plan, and in there, they have 6 foundational digital capabilities that they're investing in, and AI and robotics is one of the 6 of these foundational digital capabilities. So there are some resources and priority that government is putting into this area. We've also now have a dedicated AI research conference, which is increasingly drawing people from industry. It's the South African Conference on AI Research. If you don't know about it, it's happening in December in Stellenbosch. And the other very interesting thing, if you're interested in this kind of community and ecosystem space, South Africa will be hosting the International Joint Conference on AI, one of the premier AI conferences in the world. It's the first time in Africa, and it will be in Cape Town in August next year. So underneath all these ecosystems are research networks, and all of you know NITheCS, and it's more encompassing than just AI. It's quite a massive, I think it's grown massively, but we also have a much smaller but dedicated interdisciplinary AI center. It's called the Center for AI Research, and there you can see some of the universities involved in it. And it's also with the CSIR, and it's linked to DSI's decadal plan. So CARE is a strategic partner of NITheCS, and I think this is quite an important step to actually connect the current networks that are in place in terms of the ecosystem. And where else can we go? So we also have some lessons learned from health information systems, and we tried establishing an ecosystem over quite a few years in South Africa. And it was through the Center for AI Research. This was at UKZN. And it was all about finding problems. Again, these were like, had a social impact. And this was about creating public health information systems, large-scale national level public health information systems. And we partnered with an implementing partner, company called organization called JMB Health Systems. They worked in South Africa, Mozambique, and Rwanda. So they would find, they actually were designing and implementing systems. They would feed in the requirements and challenges. We had an applied group, and we had some theoretical groups. And then we constantly followed, and we managed to actually get a few technologies that were actually deployed in the real world. But this is of course quite hard. So there are some experiences that we can draw from. So the one recommendation behind just the networks is infrastructure. And here I'm talking about standards for, and this is based on our experiences working in the National Health Information Systems. So you need some kind of standards or guidelines for data and interoperability, some protocols for communication, and some frameworks, some national level frameworks that are supported, and then we can train people for the next 10 years on some reference implementation so you can see how to implement these things. And of course, there's lots of benefits to making all of this open source. One very successful technology that emanated from that ecosystem is the Open Health Information Mediator. If you're interested in this, you can go and read more about it at the OpenHIM website. Another aspect is how does all these, now you've got government, should government now direct it, and then what happens to innovation and how that they might be very slow. And based on experiences in on the health side over several years, there's this notion of a middle-out approach to ecosystems. And what you do here, or how this works, is you have the government setting up regulation bodies and so providing oversight. So they play like as a facilitation mediator role. And then you still have the space for the bottom up, the small startups, the provinces, the NGOs to actually, so they have the space to innovate. And this kind of both bottom up and top down, it's called a middle out approach. If you're interested in it, you can read about it more here. Seems to have worked really well over the last 10 years for building up these kinds of complex innovation ecosystems in many countries. So my concluding thoughts, setting up ecosystems, especially cross-institution research and innovation networks, is hard work. So if you want to know how to speak to Francesco, he's been involved in NITheCS, and I have a lot of respect for what he's done and because it is really difficult coordinating across institutions, across people. But it's possible. Bridging the gap between academia and industry is challenging. Again, it is possible, but again, it's something that we have to navigate. But I do think that government can play a key mediating role in this kind of middle-out approach. And they can set the terms of reference and set up a strategy, a long-term plan, and an enabling environment. And then it can bring academia and industry together in a more structured and coordinated way. So those are some thoughts, and I hope that you have found this hopefully a bit stimulating and have some ideas about how we can move forward in the space. Thank you.
Dear Deshen, thank you very much for your very nice talk.